Alright folks, today we're going to talk about the notes on simple harmonic motion and waves. And while they are somewhat different in application and description and maybe where you would see them in nature and so forth, they do have some similarities. So I'm going to kind of go through, talk about some of the equations, characteristics of, and do a couple of example problems. And again, you guys can use these for future assignments or tester quizzes here as we move forward the next couple of weeks. So first question is focusing what is simple harmonic motion, and it can be represented by any sort of an object that has both an amplitude and a period. And you will find a common theme between this and when we start talking about waves also. An amplitude has to do with how far something oscillates, how big the oscillation is, and then the period itself talks about the time it takes for it to happen. So some frequencies or oscillations happen very quickly, other ones are very slowly, and some amplitudes can be very large and some can be very small. So one of the most classic examples talking about things that are a simple harmonic mover or a demonstration of simple harmonic motion would be the pendulum. So all a pendulum is some mass suspended by some sort of a string that can just oscillate freely in gravity. So this could be even like a swing set. Common things you may see a pendulum in is like an old pendulum clock, like a Godfather clock or something like that. And there's one of the most common equations that goes along with the pendulum is how to calculate the period of the pendulum, predicting how quickly it will make it back and forth to its amplitudes. And it looks something like this. And they would say that the period of a pendulum, which the period is represented by t, the period of a pendulum is the time that it takes for it to make one full oscillation all the way from left to right. And this is represented in terms of seconds. And on the right hand side of this equation, it's got 2 pi and then the square root of L over G. The only two variables that will influence the period of a pendulum would be the actual length of the pendulum, which would be measured in meters. And so the G represents gravity, and this is generally going to be representing the acceleration of gravity on Earth, which is 9.8 meters per second squared. Now it is possible there may be some scenarios where we would say, hey, there's a pendulum on the moon or a pendulum on some other planet where there's more or less gravity, but for the most part that's going to be kind of what we would stick to. Other examples of simple harmonic motion would be talking about springs, oscillations in springs. So classic examples are just suspending a mass from some sort of a spring that can be stretched. This could just be hanging from the ceiling, whatever it may be. There's some applications of Hooke's laws, which will relate force to spring constants and distances that the spring is stretched. And generally speaking, what this means, where the force equals mass times acceleration also equals this negative kx. The k is talking about some sort of a force per distance, so it's a Newton per meter that the string produces. So generally speaking, things that have a high spring constant would mean the spring is difficult to compress or stretch, and things that have a lower string constant would have a lower force to move, like a softer spring, so less force for a greater distance. And below it are some equations to do some calculations with the frequency of these or the period, which are basically just inverses of each other. Again, we talked about the period being the time it takes for a full oscillation to happen, where the frequency is how many oscillations happen within a given amount of time, which they would typically say per second. So if a spring oscillated at 5 hertz, it would be that many oscillations per second. So every single second it would oscillate 5 times. So some things like this would probably have very low frequencies, but when we start talking about light or sound and even other types of radiation and electromagnetic waves, they can have frequencies that are extremely high because they oscillate back and forth thousands of times per second, if not more. Okay? Moving on to talking about what are waves. Just generally speaking, a wave is something that carries through space or matter. So there's different types of waves, which we'll look at here a little bit more closely. But when a wave travels through matter, it means that it actually physically collides with other particles, and then that particle hits the next particle, kind of like a chain reaction. And those types of waves, the ones that do travel through matter, are known as mechanical waves. So they'll say they travel through matter or medium. So examples of that would be sound waves or earthquakes, water waves, surface waves. They're waves that cannot travel through a vacuum. For example, if you go to outer space, these things do not exist in the emptiness or vacuum of space. If you are in space and you clap your hands, try to produce a sound, you cannot produce sound because there's no particles to be bouncing from wherever the source of sound is to the receptor of sound, whether it's your ear or a microphone. It just is not possible because there's nothing there. Same idea with like water waves or earthquakes. Well, not to say that there aren't maybe earthquakes or things on other planets, surfaces of planets inside of, where there is matter, but in the emptiness of space, there's nothing there to make those collisions or actually produce the waves. However, electromagnetic waves are kind of a special type of wave. They can go from point A to point B without being inside of matter. And you'll see some of the examples that are given here are often what you would maybe find in the vacuum of space, which is part of what makes emptiness of space to be quite dangerous. Light waves, well, obviously we get light from the sun and some other radiation from the sun that actually makes it to Earth, which isn't always so harming. I mean, you can be exposed to ultraviolet light and you can maybe get burned. Radio waves, X-rays, and other types of high-frequency radiation. Now, some of these, on the other hand, if you're in outer space and you're being exposed to high levels of radiation from the sun and other sources, that's not a very healthy thing. So, fortunately on Earth we have a magnetic field and we have an atmosphere which protects us from a lot of this stuff, where astronauts on, say, the International Space Station or that go further out into space are somewhat subject to that, even within the confines of their shuttle. But if you could exist in the vacuum of space based on temperature and pressure, which you can't, but if you could, there would still be a lot of other problems to deal with, and a lot of those would be in the form of electromagnetic waves. Breaking those categories down, electromagnetic waves and or mechanical waves, there's different models that we use to represent different types of waves. So the most common model that people probably see from place to place is the transverse wave model. And those are waves that they would model as moving perpendicular to the direction that they travel. So if this was a wave moving from left to right, they would say that the particle itself will oscillate up and down as it moves from left to right, causing kind of like a sine or cosine type wave or motion across the paper. And there's physical attributes to this, similar to how we described waves at the beginning. Remember, we did say that waves have to be, or even things in simple harmonic motion would have some sort of an amplitude or some sort of a period. Amplitude of a transverse wave is going to be measured from basically the middle point here, kind of a neutral point, all the way to the peak, or from that neutral point down to the trough. So they would say the amplitude falls somewhere from here to here, or you could say from here to here. They should be equal and opposite from the point that we measure zero from. We would also talk about waves having characteristics of wavelength and velocity. So a wavelength on a transverse wave has to do with the distance between any two common points. So in this picture they describe that as being from the trough to the trough, or the bottom to the bottom. You could just as easily measure wavelength from the peak all the way to the peak, would be the same thing. And we represent wavelength with a symbol known as a lambda symbol. It kind of looks like a backwards H of some sort. But that is a very common variable that we're going to use in a lot of example problems. We have some equations down here below where we will relate frequency, velocity, wavelength, and period all together. And they all kind of play off each other. Again, the velocity of the wave traveling from left to right also comes into play when we're dealing with wavelength and frequency. And we'll look at that here a little bit closer in just a couple of minutes. Longitudinal waves have some similar characteristics to the transverse waves. They do too also have a wavelength and potentially amplitudes. So the wavelength in a compression type wave or a longitudinal wave, this is more, if you could imagine getting like a slinky and compressing one part of the string and letting it go, and then watching the spring compress and extract at various points along the line, you could still measure the wavelength from any start point back to that same repeat in the pattern. So if they measure it from the point of compression to the point of compression where the springs are closest together, wherever it gets back to that same point, they would measure that as the wavelength. You could also measure it from the distance where the spring is furthest apart if you wanted. Either one represents the same thing. But these types of waves, again, we talked about a sound wave being a type of longitudinal wave, or earthquake waves potentially basically buddying end to end. So the one in front making contact with the one behind and so forth. And then there's also surface waves, and a surface wave can be more like, it can be oftentimes visualized as a cycle or a wheel that rotates around. And this is a common misconception about, say, waves out on the ocean. If any of you have ever been in a boat sailing or been outside when it's windy, I think we all know that, you know, the wind can definitely move you around the water. So if you had a motor and turned the motor off, and whether you had a sail or not, if the wind was blowing, you know, in this direction, there'd probably be some waves on the water, and your boat would probably drift in the direction of the wind, which is true. But I think the misconception there is, you know, is it just the wind that's moving you, or is it the waves that move you also? Well, in a perfect world, if you could make waves without wind, maybe in a wave table or something like that, if the waves were just moving as surface waves moving up and down, and there was no wind, I guess it's kind of the question, a little tricky, is would your boat actually move in the direction the waves are moving, or are the waves really moving from, say, left to right? Like, what's really happening there? So oftentimes they will use these circles to kind of show what is really happening with the wave, and this is kind of what they say would represent it. There's a small fixed point on each one of these wheels, and as the wave goes up or down and passes through, you can't necessarily think of the water as moving from left to right, traveling at any given velocity. You got to think of the water kind of cycling up, cycling down, cycling up, and cycling down. And if you could maybe even go out and put like a volleyball or a beach ball, again, no wind blowing, but just the wave moving. If you threw the beach ball out into the middle of the waves, would the wave move, or would the ball move, or would the boat move? Well, in essence, the boat wouldn't really move in the overall sense. It'll go up and forward, and it'll come down and go backwards. It'll go up and forward and down and backwards. Just keeps cycling around on this endless cycle, not really moving forward, not really moving backwards. So and it's kind of hard to visualize with this picture because the picture is moving from left to right, but what they're trying to show is the wave moving from left to right. If you were in a boat, you would go up and down and forward, and then you would go down and back and up and forward and down and back and up and forward. So the boat would actually move around in a circle like this, as would the volleyball or the beach ball, whatever you're using, assuming that there is no wind. If there's a wind, of course, the wind's physically dragging you across the wave in addition to that. So, but it's the same thing. We can still measure amplitude. We can measure the period it takes to get around. We can measure wavelength, how far, you know, across are they. So there's a lot of similar applications even between the three various types of waves. So these are the basic wave equations that you guys are going to use. So when you're looking at the different variables here, V is velocity, F is frequency, and the lambda is wavelength, and then the T will stand for period. So as we go through and we look at some of these, we know that the velocity here is measured in meters per second. The lambda, or the wavelength, is going to be measured in meters. You're going to have the frequency, which is measured in hertz. You're going to have the frequency, which is measured in hertz, which is the same thing as 1 over S. And the reason I put this up here is because frequency and period are inverses of each other. So when we talk about T as a period, and I know oftentimes people see the T and they think of time, which is okay, very similar as to what they're measuring. That's just a second. So you'll see here that frequency is 1 over the period, or period is 1 over the frequency. A hertz is what we describe frequency in, but it's 1 over a second. So if you took the inverse of 1 over a second, you're just going to get a second. So that's the relationship between all of these. Still using all of our standard units for common variables that we have used in the past. So I'll go through a couple of these examples using some of the equations that we got. So try to follow a lot of the same procedures anytime you're solving physics equations or written out math problems. You want to list the variables and the information that they give you, determine what equation you're going to use, and then go back and solve, and then kind of check for understanding to see, do these results make sense. So we'll start out with some kind of basic applications. Example 1 says, what is the velocity of a wave with a frequency of 10 hertz and a wavelength of 5 meters? So list what they're asking for and what they give you. So this one, we have an unknown velocity. They tell us the frequency is equal to 10 hertz. And then they tell us that the wavelength of this wave is equal to 5 meters. So if our velocity is the unknown and they give us frequency and they give us wavelength, you want to list the equation that we're going to be using. There says velocity is equal to frequency multiplied by lambda, or wavelength. So we're going to take the frequency of 10 hertz, and you're going to multiply it by the wavelength of 5 meters. And this is going to be 1 over an s times a meter, so that will give me meters per second, and the 10 times 5 is going to give me 50. So if this was the case, if that was the frequency of the wave that we had and the wavelength that we had, then the wave would have to be traveling at a velocity of 50 meters per second. For example number 2, they're asking what is the frequency of a wavelength. They're asking, for example number 2, they're asking what is the frequency, so that's your unknown, of a wave traveling at a velocity of 40 meters per second and has a wavelength equal to 2 meters. So again, we got some common variables there, but the equation that we have to use is rearranged a little bit from the previous. So now we're going to look at frequency being equal to the velocity divided by the wavelength lambda. So you take your velocity of 40 meters per second, and you're going to divide that by the wavelength of 2 meters. And you can even kind of see how the meters are going to cancel out, and all we're going to be left with is a 1 over a second, which 1 over a second is the same as a hertz. So 40 divided by 2 gives me 20 hertz, or 1 over s. So for example number 3, they're asking us to find the period of a wave that has a frequency equal to 0.01. So the period is unknown, but they do tell us that the frequency is equal to 0.01 hertz, which is a very low frequency. Do keep in mind that period and frequency are inverses of each other. So basically, if you can kind of do the inverse of whatever's already there, it should give you the answer that we want. So we know that the frequency is 0.01. If you do 1 and you divide it by 0.01, that gives you 100 seconds, which again, a very low frequency. So it would take 100 seconds for this cycle to, say, repeat itself. So even if this was a wave, if you could imagine like the crest of one wave happening here and then 100 seconds later it crests out again, that would be quite a low frequency. Alright, now we're going to talk about how waves interact with either each other or other objects that they make contact with. So waves can do a lot of different things. They can bounce off objects, they can go through objects, I guess in some instances they can kind of go around objects. Interference is a common way that waves can interact with each other. There is generally constructive and destructive interference. Constructive interference is when two waves are added together and the amplitudes are maybe in the positive wherever they overlap, where they're transposed, and it can actually make the resultant wave larger. So it would kind of be like having two speakers instead of one. You have a 10-inch subwoofer here and a 10-inch subwoofer here, and they're both producing the same sound, same frequency at the same time. The two speakers should be twice as loud as the one, assuming that they're producing, the same amplitude and frequency and everything. However, there is something known as destructive interference, where you could take two sound waves of equal amplitude, but if their phases are opposite, so one's at its maximum while the other one's at its minimum, when they collide with each other, in essence, the positive 10 could cancel out with the negative 10, and and vice versa, and you're going to get a result in the wave that's actually a 0. Cancel out the one that was already there. So kind of interesting. And then other types of interference. This is supposed to represent single and double slit interference patterns where single wave fronts can go through small openings or portions, and you'll see that the wave will actually scatter. And there is something known as Eugene's principle, which says that any wave front is actually made up of a smaller wave, where the front of the crest of the wave comes. So if you can, in essence, just go and pick out a small section of that wave front, from that point it will radiate its own wave. So you potentially maybe see examples of this if you've ever sat on the edge of a shoreline and watched rocks deflect small ripples or waves that come in. If there's a single rock out in the lake and a small wave goes by it, you might get a ripple off of that, but if there's other rocks around, they might ripple off of that, and again the pattern just kind of continue. It's like off of any given point you might see the waves kind of radiate away from each other. So what they're trying to show is you got what is a wave really made out of. Potentially it's made up of a lot of other small waves. So when you send through the one slit, these lines are supposed to represent maximum and minimums in the wave, and then if you have two sets of those waves, there's places where they overlap. You can kind of see where these sections crosshatch, and you get constructive and destructive interference, what they would call interference patterns here, where all the high spots would be constructed and the low spots would be destructive. So they're all at minimums at those given points. So kind of interesting. Waves can have apparent changes in their frequency. So you guys have probably heard of the Doppler effect before, and the Doppler effect can be applied to light waves or sound waves. Probably is the most common application. Basically what's happening is if the wave source, whether it's light or sound, is being emitted from an object that is moving relative to the object that is receiving the wave. For example, a person who is either listening to the sound of a train drive by with a whistle, or if you were observing light coming from some source, if that light was coming toward you or going away, the apparent frequency of the wave going into your eye or into your eardrums can either increase or decrease based upon that relative change in distance. So if everything in the universe was stationary, relative to each other, even if we were all just on one big disk spinning around and everything stayed at the same distances from us, when we viewed stars, the color of that star would always be its true color, and sounds would always be the true frequency that's being produced from whatever that object is. But the reality of it is things are moving. Some are moving away, some are moving toward us, maybe they come toward us and then away. So the Doppler effect has most commonly been demonstrated probably by like a sounding alarm or a siren driving by. If you've ever heard an ambulance or fire truck come toward you, and then as it goes away, when it's coming toward you, it sounds as if the sirens have a higher pitch, and then as they go away, it sounds as if the sirens have a lower pitch. And the reason for that is the direction that the object is moving. So in this situation, they're saying the train is moving from right to left. The sound emitting from it, from that solo point, is producing one frequency, but as you move into it, the velocity of the train itself is compressing those waves. So they're showing this here as a blue shift, but this is going to represent a higher frequency. And in terms of sound, this would be a higher pitch, and in terms of color, it would be a more violet or blue color on our spectrum of visible light. Lowest frequencies that we can see are down into the yellows and reds, and the highest frequencies that our eyes can see are in the purple to violet. So beyond violet is what they would say is ultraviolet, which can be damaging to the skin, and anything below the red is considered infrared, which is not so damaging to our skin and so forth, but it's still below what our eyes can receive as a detectable frequency. And this, on the world of the electromagnetic spectrum, is an extremely small sliver in the lowest and highest frequencies of waves that we measure. However, on the other side over here, we talk about what they would call the red shift, and this is where the frequencies are actually produced to be lower because the wave itself is being stretched apart. So based on the characteristics of waves, things with high frequencies would be closer together, oscillating up and down very quickly. Things with low frequencies would be stretched out, oscillating up and down maybe more slowly. So this is a general characteristic of what the Doppler effect is. There's many applications that we will look at further in the future. Behaviors of waves that either bounce off of objects or travel through objects, because some objects are transparent. This is known as refraction and reflection. So the first example here, which is going to demonstrate a little basis of what Snell's law is, this has to do with light bending as it travels through objects. So you have to think of objects that are transparent. Some of the most common applications we'd have there would be glass of the windshield of a car, water in a cup, maybe a glistening diamond in a ring or a piece of jewelry. The light can actually go through it, pass through it, and comes out. But the thing that's interesting is that as when it goes through the object, it can speed up or slow down. It can change velocity, which also can change the direction of the light as it goes through. So this example here is showing light going in or out of a body of water, and you'll see that the angle coming out from what they would call normal or the vertical is greater than the one inside of the water. So if you've ever tried to look inside of a bucket of water, and if you tried to touch an object beneath the surface, you get a very skewed perspective on where the object really is. For example, if there was an object located right here, you would actually envision the object to be located right here, because the light coming out would bend as it speeds up going through the air, which has a lower index of refraction, and your view on where the image is actually makes it appear to be out further than it is. It's actually more down or underneath the surface than normal. And we'll do a couple of examples of Snell's law here in the future, but basically what it's saying is n1 times the sine of theta 1 equals n2 sine theta 2. N is the index of refraction for one type of material, and n2 would be the index of refraction for another type of material. And these are set standards which you would look up in a data table for air and water and glass and acrylic, plastic or diamond. They all have different index of refractions. And then the sine of theta is you're taking the sine of the angle away from what they call the normal, which is the vertical line perpendicular, shouldn't say vertical, perpendicular to the surface. So if the surfaces were horizontal from each other, the normal line is perpendicular to the surfaces that are making contact. And body or the water. So if we scroll down below, we'll do a little application here on example number 4. It says, assume that a ray of light is traveling from air into the water, just like our example up above. What is the angle away from normal of the wave in the water if the normal angle of the light going through the air is 25 degrees? And you will see here they have a list of the index of refraction for the various objects, and we're going to be focused on air and water. So we're going to be looking at these two. So in the picture up above, I'll kind of diagram what we're doing. They're basically telling us, and I'll get rid of these for now. Basically what they're telling us is this angle here is equal to 25 degrees away from the normal, which is perpendicular to the surface. The index of refraction for the air is basically 1. It's 1.0003, and the index of refraction for the water is equal to 1.33. So they give us the n for this and the n for that, and they want us to figure out the angle in the water away from normal based on our 25 degrees going in. So down below we're going to list for our equation. So our base equation says if you take the index of refraction of one item and multiply it by the sine of theta for that same item. So this is the index of refraction for the air, and the angle of the air is going to be equal to the index of refraction for the water, multiplied by the sine of theta for the water. And we're going to be rearranging this equation to solve for theta of the water, because they give us the n for the air, they give us the theta for the air, they give us the index of refraction for the water, and we need to find the theta for the water. So if I rearrange this equation, I'm going to get something that looks kind of like this. It's the index of refraction of the air multiplied by the sine of theta for the air. It's just this. I need to divide both sides by the index of refraction for the water so I can get this to cancel. So I have the index of refraction for the water on the bottom here. Then I still need to get rid of the sine over here and just leave the theta of water by itself. So the only way to get rid of the sine by itself is to do the inverse sine of the whole value that's here. So I'm going to do the inverse sine of that, and this will equal the theta of the water. So let's plug in the values that we got. Index of refraction for the air is equal to the 1.0003. The sine of theta, which is 25 degrees, for the angle going in, and then the index of refraction for the water is equal to 1.33. Now I should be able to make a prediction based upon the diagram and the index of refractions that they gave us. You can notice that the angle away from normal or perpendicular of the light going in is greater than it is for when it's traveling through the water. The light will slow down as it travels through the water, and on the wave front, as it makes contact with the surface, that slowing down of the first portion of that rounded wave that touches slows it down, therefore changing its direction a little bit, shifting its direction more inward. And I would make a prediction that this is going to be lower than 25. So plug in the numbers and let's see what we get. You have to get the sum of everything inside of this first, and then you got to take the inverse sine of what's there, and then when you're done you should get 18.53 degrees would be the angle away from normal. That would be the value down here, would be the 18.53 degrees, which does kind of match our prediction of what we were looking at before. And then this last example, we're not going to do any math stuff with this, but we're just going to talk a little bit about the nature of objects that reflect. So with reflection, some of the concepts are pretty basic. They're still measuring this normal perpendicular to whatever the surface is. They have a light ray coming in and a light ray going out. And the main thing to remember with reflections is the angle of incidence. So the angle coming in from normal is equal to the angle of reflection, or the angle away from normal going out. So if this was 20 degrees, they would say this is 20 degrees. Or if we dropped the angle to be a little bit lower and you measured from here, it was more like 70 degrees, it would bounce out at 70 degrees. It would be just equal and opposite. So that's a quick overview. It's a lot of information, but there will be more examples to come into the future. So we'll start with some of the more basic stuff from the beginning and then work our way over the next couple of weeks through the rest of the concepts in the notes. So we'll have some assignments and things to practice and other video examples to follow. So I appreciate it. If you guys got questions, please feel free to contact me. Otherwise, have a good week. Thank you.